Now, now the Roche theorem is if fx is a function such that first member fx is continuous, fx is continuous in closed interval AB, and second, fx being function is differentiable in open interval AB, and third, fx f of A is equal to f of B, then there exists at least one point C belongs to AB, such that f dash C is equal to 0. Now we shall prove this theorem. Here two cases arise. Fx are the two types of function, first constant and second non-constant. Then case first, if fx is constant, then it will be f dash C is equal to 0 for all C belongs to A. So it will not be constant. If function is constant, then second case, the function is non-constant. If function is constant, this is all time will be 0, whose derivative will be 0 for all points C belongs to AB, then nothing will be proved. So we will consider fx is a non-constant function. If fx is the non-constant function, then the virtue of third f of A is equal to f of B. It means function first will be increase or decrease. If fx is a non-constant, function, then by virtue of C, it will be increase first or it will be decrease first. It will be increase first or decrease first. If we consider function will be increases, if we consider the function will be increases, then after some time it will be decrease, then after some time it will be decrease, since f of A is equal to f. If we consider the function is increase first, if we consider function of increase first, then we make a graph with increasing function like this. Now this is point A and this is point B. This is A, f of A, and this is f of d, f of a and f of t. Now this is the point of C and this is the point of C minus H and this is the point of C plus H where C belongs to AB. From the diagram we notice f of C minus f of C minus H, f of C minus H, this is greater and this is less, is always greater or equal to 0. And f of C plus H minus f of C, where f of C is greater and f of C plus is less, so it will be less than 0. Again this can be written as f of C minus H minus f of C is less or equal to 0 and f of C plus H minus f of C is less or equal to 0. Or we can write this f of C minus H minus fc upon minus H is greater or equal to 0 and f of C plus H minus fc upon H is less or equal to 0. Since H is very close to C, so we taking limit H tends to 0. Now taking limit H tends to 0, then this is limit f of C minus H minus fc upon minus H is greater or equal to 0 and limit H tends to 0 f of C plus H minus fc upon H is less than or equal to 0. So we can write this can be written as L f dash C is greater or equal to 0 and this can be written as R f dash C is less or equal to 0. So that implies we can write f dash C is equal to 0 where C belongs to open interval AB. For all C belongs to